All right. So this is the main course content of our complete analog design course. Okay. So the module one. Basically we are trying to cover different categories of people to address their understanding on the analog circuit design. The very first category of people are the students who are like fresh graduates from the college, or it could be graduation or undergraduation or post graduation. Okay. So to it's not only like the students from they should be from electronics background, so they could be from computer science, they could be from electrical, they could be from telecommunication, instrumentation. So they may not be having much knowledge about analog circuit design, from where to start, how to start, that kind of stuff. To address such kind of people, this course content is been designed. The second category of people are like actual industry professionals. They have just started their career into analog circuit design, but they don't know how exactly, because it's a totally new field, right? They don't know how exactly to start with, and from where has to be started, and what are the understanding minimum basics needed to start their career. To address such kind of people, this course is also have been designed. The third category of people that we are addressing are the industry professionals again, but they're not into analog circuit design domain. They're into some different domain. For example, it could be layout design, or it could be physical design, it could be software, it could be embedded, but they want to switch their career from existing domain to analog circuit design domain. So how to switch that? So what is the minimum basics needed for switching this? So to address all these categories of people, we have designed this course content. All right. So let's start with the first module, that what we are studying and what we are addressing here. As we all know that analog design is nothing but it's pure like semiconductor design. So basically we are dealing with the transistors, MOSFETs, diodes, BJTs, right? So it's everything is it's all about basically to know more about semiconductors and its corresponding devices and applications. So that's why we started with the device physics, where we study about semiconductors, what are the types of semiconductors, when to use what kind of semiconductor. So what are the different components, for example, BJT, MOSFET, diodes, what are their basics, how exactly they operate, and what are their characteristics, when to use what, that's when to use diode, when to use MOSFET, when to use combination of both, right? And small signal model of it. So this is very important topic, small signal model, because so whenever we use MOSFET, especially, so let's say we MOSFET we use as an amplifier, right? So we are not dealing with very large signal there. It's very small signal, which is in terms of 1 microvolt, 10 millivolt, 1 millivolt peak to peak value. So how exactly these circuits or these devices behave for those small signals? It's very important to understand that small signal model for amplification is concerned. So we are teaching, so how we exactly find out the small signal out of big circuit. All right. So how to know, how exactly by looking at the circuit, you should be able to know, tell, yes, this is again, this is what the impedance it is facing, this is what it will happen. You should be able to develop that kind of expertise once you complete this course. So that's what the main motto. That's what finally industry needs, right? So no one wants you to calculate something, use pen and paper, derive some equations, and finally, yeah, yes, it is solved. Something like that, no one is expecting. It is all about intuitivity, and how easily will look gather the information out of the circuit and tell the conclusion. Oh, this is what this circuit will do. Right? This is what, if we do this, this will what happen. This is what will happen. If we don't do this, this is what will happen. So this is what the industry expects. So that's what we are teaching you guys here. Right? The coming to the next topic in the module 1 is a short channel effects. Nowadays, industries are talking about very small channel lengths. Like Samsung will talk about 4 nanometer, TSMC will talk about 3 nanometer. What exactly that 4 nanometer and 3 nanometer? What will happen if we go lower and lower? So what are the side effects? How to overcome such kind of effects in our circuits? Right? So all these you can see that whatever I am talking about, these are all related to industry. That to advanced topics. That's what we teaching you guys here. Okay. In the here, right, we have mentioned something like teaching hours and lab hours. So the teaching hours is a theory hour. Lab hours is a lab. Actually, we do hands-on in the Cadence software. All right. So I'll tell everything. What are the softwares? What are the technologies? And how exactly we execute those circuits at the end of this module content completion. Okay. The very second module is the tool introduction, where exactly we are drawing the schematic symbols and running the different simulations. Okay. So for example, AC simulation, DC simulation, transient simulations, and how to analyze those results. It's not like we just run and leave it. So we should be able to tell that circuit behavior by looking at the waveforms. So this is what is happening. That's what finally experts do, right? So by looking at the results, so they will tell, oh, this is what where it is going up. This is what we have to fix, right? So this is where the fundamentals of the such expertise will start here. Okay. So after here, basically, as I mentioned, that circuit schematic drawing, creating the symbol, doing the different analysis on the circuit we have drawn, and running the different simulations. Okay, so you can see based on the module, the number of hours will be allotted. So here in the cadence tool, the theory is not needed much here. So we just use some manuals and we just familiarize some different options. But how much you do on the hands-on in the lab will actually carries more weightage. So that's why we kept more hours for the lab than the theory. All right. Coming to the single stage amplifiers. So this is a building block of all amplifier designs. So we use these two models and we build single stage application on top of these two module knowledge. All right. So here basically we are talking about one stage amplifier. That's what the single stage amplifier means. So here we talk about common source amplifier, common gate, common drain, that is source follower. What are the advantages and disadvantages of each single stage amplifiers? And if there are any disadvantages, how to overcome them. So that's how this cascade stages design will come into picture to address the disadvantage of the common source amplifier. Okay, you can see the number of lab and theory hours. Actually, lab hour will be actually equal or more than theory hours. You can see, right? So that is why we give more weightage for the labs, which is hands-on, so that you guys will carry more information and you guys can understand better these circuits. Okay. The more you do the lab, the more you understand. The more understanding will be there, and more better conceptualization of your understanding. So whatever you understand, you can imagine, oh, this is circuit, this does this. So if I use modifier something like this, it will behave something else. So that you should be able to visualize such kind of results. All right. Coming to the module 4, this is so some part of this differential amplifier is taken from the single stage itself. If you break this differential amplifier into parts, you will end up finally into single stage amplifier. So here in the differential amplifier, why we go for differential? That's what single ended versus differential does. And current mirrors, which is very important and very most commonly widely used topic across all analog design, is current mirror. So we are doing different types of current mirrors, both in theory as well as lab, and designing the differential amplifier and doing different analysis on top of differential amplifier. For example, DC analysis to make sure that your operating conditions are proper, AC analysis to know the gain plot and phase plot, Bode plots, and transient analysis to know the time domain behavior, and pole zero analysis to know the number of poles and zeros of your circuits, and stability analysis to know the whether your system is stable or not. If it's not stable, how to make it stable. There are lots of analysis we do here. So I'm just mentioning few so that you guys can get some idea or some picture about it. Okay. So this is what the differential amplifier. Then as we know that most of the amplifiers will work only when there is a proper feedback and proper stability is applied to that particular circuits. So here in the feedback circuit, so we are talking about different feedback topologies and different feedback practical applications. So when to use what kind of feedback in our application, right? So those stuffs will be taught here in this feedback technique concept. Okay. You can see there is no lab for this feedback because these feedbacks will be used and implemented in the operational amplifier, so that these theory knowledge is needed for this op amp. That's why we are kept feedback technique and stability before the op-amp. Okay, so the stability analysis. So what are the stability analysis? What are the frequency component compensation technique that we use if the circuit is unstable, right? What are the different compensation feedback techniques we have? How to build the feedback system? So these two are the theory topics. Okay, so we are using these two topics concept plus differential amplifier design concept to build the op-amp. Okay, you can see the op-amp lab hour is, sorry, theory hour is 6 hours and lab is 9 hours, 6 plus 3, because we are using these two concept techniques and implemented in the op-amps. That's why it needs more lab, more hours of lab, so that to proper understand these concepts and implement same in the lab, right? So that's why we have kept more lab hours for this op-amp. So here op-amp, so we are building single stage, two stage op-amps, cascode, folded cascode, gain boosting op-amps, right? These are all like very advanced topics and most commonly used the op-amps in the industry, right? So we'll be studying when to use what op-amp, right? So it's not like only one op-amp is used commonly for all the applications. Each and every op-amp topology, for example, cascode, folded cascode, and gain boosting, they have their own advantages and disadvantages, and they have corresponding applications as well. So we have to know when to use what op-amp topology. So that's what we are understanding in this particular module 7, that is op-amp design. All right. So once we complete this op-amp, so this is where we are building industry standard applications from module 8. So voltage regulator design, right? So I'll give an example of your laptop. So I think you guys have connected either by laptop or desktop or a mobile phone. Everything has its own, operating voltage. For example, if you take your mobile phone, it has some 3.3 volt as a battery, somewhere around 3000 or 4000 milliamps hour as your battery rating. So what is a 3.3 volt? So who defines that? And if the 3.3 volt is applied, given to, if 3.3 volt battery has been plugged into your phone, so how exactly that will be converted to the processor? For example, your processor may be Qualcomm Snapdragon or some iPhone or some Samsung processors. So it needs its own operating voltage. For example, most commonly it will be around 1 or 1.2 volt supply. So from 3.3 volt battery to 1.2 volt has to be converted internally. Who is converting that? How to do that? That is what this exactly voltage design, regulator design, we are doing it here. Okay. So basically conceptualizing this voltage regulator design here, and design is low dropout regulator, which is commonly used across all SoCs. When I say SoC, it's a system on chip. For example, your Qualcomm Snapdragon is a SoC. And Intel Core i3, Core i5, Core i7, it's a SoC. It has its own operating voltage spec. Intel will operate at 1.8 volt. Snapdragon may operate at 1.2 volt. Right? So that's what. So to give that 1.8 volt, 1.2 volt, sometimes 0.9 volt, who is giving that? This guy will be giving that particular supply to your processor or a SoC. Okay. So we are saying that here. You can see theory hour is 4 hours. You can see lab hour is 6 hours here. Because we have to build everything at the transistor level, which is from the scratch. So we'll be deciding what is the W should be there for each and every MOSFET inside this regulator. Okay. After this, definitely bandgap references. This is also most commonly used application across most of the analog industries. Okay. So here we are talking about a temperature independent reference circuits and bandgap reference design. Here the bandgap reference is nothing but your both voltage reference as well as current reference. So we are designing it in the theory and we are seeing those results in the lab as well. Okay. So this is with respect to the voltage is concerned. So then next comes is operating frequency. Again, I would like to take the same example of previous. For example, if your mobile phone is using this Qualcomm Snapdragon, or your laptop is using somewhere like Intel Core i3 or Core i5 or i7, it has its own operating frequency. For example, if it's Core i3, it is 2.3 gigahertz. So what is the 2.3 gigahertz? Who is giving that? So 2.3 gigahertz is the operating frequency given by this particular oscillator who is sitting inside the phase lock loop. Okay. Now it's a second application. So what are the positive feedback concept? Because oscillator needs positive feedback. And what is it concept? And how to design the different oscillators like ring oscillator, voltage controlled oscillator, which is commonly used in the industry again, right? So this, whatever the oscillator is there, this is part of a PLL. This is a complete system. So PLL concept, PLL design will be understood here. What are the different types of PLL? Phase type 1, type 2, right? Okay, so those stuffs will be studied here. So coming to the last part, that is data converter. So this is again one more applications that we are seeing that in this complete course content, for which there is no lab for it. Okay, so data converter is basically like analog to digital converter and digital to analog converter. So I would like to give example again. So I'm talking here through the microphone. So that will be converted to the my voice is basically analog random signal, which has no finite amplitude, but it varies over the period of time. So this voice will be converted to digital through the analog to digital converter, and that will be fed to the processor for the processing. Now the processor will take your digital converted signal and processes whatever signal conditioning or some addition of the bits or some random bits addition, so that it can be transmitted to the channel. Once the processor transmit my signal over the channel, so you guys will be taking your processor will be taking my voice, which is digitalized, encoded digital format signal, and processor, what it will do, it will remove that encoded format and gives back the digital signal out of your processor. Now some guys will be sitting on your laptop who will do the digital to analog conversion, and that analog converted signal will be fed to your earphones so that you can hear that. So this is one way. So the same thing will be applied for your end as well. So whenever you talk, I can hear that, right? The same process will goes from that path as well. So these guys, analog to digital and digital to analog converters. So what are these concepts? How exactly they work and how to design them? So what are the different types of ADCs and different types of DACs are there, and what are their advantages, disadvantages, and when to use what, which is very important. That will be understanding in this particular module. So once we complete all these modules, right? So you guys will be allowed to choose any mini project on your own. You can browse through papers wherever you want, or your area of interest. Since we covered all the topics in most of the areas, like clocking area, power supply area, and data conversion area. So you can choose any of the topic and do one application or one block and submit that as a mini project to us. We'll be giving the course completion certificate after that. Okay. This is for addressing all category of people. So once it comes to the module 14, this is only for basically freshers who don't know the industry exposure or industry experience. So they may need some mock interviews, and they may need some personal developments. For example, communication skills, or how to face interviews, basically confidence levels, and what to concentrate on interview, right? So that stuff will be taught based on the need basis. Okay. So this completes the full analog circuit design content for 16 weeks. Okay. So the main tool we are using here is Cadence Virtuoso as a design tool, where we can launch ADL, ADXL. All right. Along with in the ADLX, we can do the different simulations, as I mentioned, like AC, DC, transient, whatever you want. We can do that, analyze the results. Okay. The basic technology that we are using here is we are using two technologies. TSMC 65 nanometer and GPDK 90 nanometer. All right. So you can use the whichever you want. So I'll be showing you one technology analysis and design completely from the scratch. You can use whatever you want on your own. And lab access will be provided to you 24/7. You can sit anywhere in the world and access the lab through the VPN. Okay, we have each and individual user ID separately so that there won't be any interference between two people. Okay, you can access anytime. There is no restriction on that. So you will be given with a hard copy of this complete material. So whatever we are telling, all this 12 module set course content will be given to everyone who register for this course, and soft copy as well, not only hard copy, soft copy as well sent to your personal email IDs. Along with that, every session will be recorded and that will be posted to the link, so which you have access. You can access if at all you are unable to join that particular module or particular class. You can go to that link and you can see that particular module. So whichever you have missed, so that you will get the continuity, so that you will understand next module in better way. Okay, so this is what overall content. You guys have any questions? Please go ahead and ask questions now.
Hello, Srinivas, and thanks for going through the course content. You can hear me well, right?
I think there is some disturbance in your voice. I don't know. It's only for me.
Okay.
Or
Okay.
Yeah, go ahead, please.
Okay. I'll try to move closer to the microphone. Is it better now?
Yes, better.
Okay, so yeah, like I got a good understanding of what the course contains, but one thing I was kind of expecting is analysis of RC or RLC circuit. Is that covered in this course?
So